What if I told you that just by looking at a beam of light, not touching it, not blocking it, just looking, you change what it physically is? Not metaphorically, not poetically, literally, measurably, verifiably change it. The light you're watching right now is different from the light no one is watching, and we have the experiments to prove it. In July 2025, a team of MIT physicists published what may be the most important quantum experiment in a generation. They confirmed something that has haunted physics for 100 years. The act of measurement doesn't just reveal reality. At the quantum scale, the scale of light itself, measurement creates it. This is not a philosophical riddle. This is the foundation of every quantum technology on Earth. And once you understand what's really happening when you measure light, you will never look at a light bulb or a universe the same way again. To understand why measuring light is so strange, we have to go back to 1887, to a basement in Cleveland, Ohio. Two scientists, Albert Michelson and Edward Morley, built a precision device designed to detect the luminiferous ether, the invisible medium everyone assumed light traveled through, the way sound travels through air. Their logic was elegant. Split a beam of light in two, send one beam in the direction Earth is moving through space, send the other perpendicular. If ether existed, the beams would return at slightly different times, like swimmers fighting different currents. They ran the experiment, and the result was silence. Nothing. The beams arrived simultaneously, no matter how they oriented the device. There was no ether. Light needed no medium. And more shockingly, it moved at exactly the same speed regardless of how fast the observer was moving. That speed? 299,792,458 meters per second. Exact, defined, apparently eternal. 18 years later, Einstein looked at that number and built his entire theory of special relativity on it. The speed of light, he declared, is the only constant the universe truly enforces. You can bend time, you can stretch space, but you cannot change c. Physicists celebrated. The universe had a law, a hard limit, something that could not be negotiated with. But hidden just around the corner was a discovery that would make even that certainty feel unstable. In 1801, a British scientist named Thomas Young shone light through two tiny slits in a barrier and found something that should have been impossible. Instead of two bright stripes on the wall behind, what you'd expect from particles flying through two holes, he got dozens of alternating bright and dark bands, an interference pattern, like ripples from two pebbles dropped in a pond, overlapping, reinforcing, canceling. This proved light was a wave. It spread through both slits simultaneously, interfered with itself, and painted the wall with its own internal geometry. For a century, that seemed settled. Then Einstein showed in 1905 that light is also made of particles, photons, arriving one by one like tiny bullets. He won the Nobel Prize for it in 1921. So scientists did the obvious thing. They slowed the experiment down. Fire photons one at a time, so slowly there can only ever be one photon in the device at once, and watch what happens. The interference pattern still builds up, dot by dot, over minutes, over hours. Each individual photon somehow interferes with itself. It passes through both slits simultaneously. It is simultaneously everywhere and nowhere until it hits the detector and collapses into a single point. One photon, two slits, both at once. This isn't a metaphor. This is what the data shows. Light behaves like a wave until you measure it. Then it behaves like a particle. Now here is the experiment that broke physics. What if you put a detector at the slits? Not to stop the photon, just to gently check which slit it went through. What if you just watched? The interference pattern disappears, completely. Gone. You get two stripes, exactly what you'd expect from classical particles. No waves, no interference, just two lines. The moment the universe knows which path the photon took, the wave collapses. And this isn't about the detector physically disturbing the photon. Scientists have run versions of this experiment where the measurement imparts almost no energy at all. It doesn't matter. If any information about the photon's path leaks into the environment, if the universe can, in principle, know where it went, the interference vanishes. The word physicists use for this is decoherence. The quantum state, the beautiful, shimmering superposition of all possible paths, bleeds away the moment information escapes. This is called the quantum measurement problem, and for 100 years, the greatest minds in physics have argued about what it actually means. Does the act of observation create reality? Does the wave function collapse into one definite outcome? Or, in the many worlds interpretation proposed by Hugh Everett in 1957, does reality split, with every possible outcome happening in a different branch of the universe, and you simply end up in one of them? We still don't have a consensus, but in the summer of 2025, we got our clearest view yet into the machinery of this mystery. The United Nations had declared 2025 the International Year of Quantum Science and Technology, marking 100 years since quantum mechanics was first formulated, and the famous debates between Niels Bohr and Albert Einstein about the double-slit experiment that followed just 2 years later. In that centennial year, a team at MIT performed what they called an idealized Gedanken experiment, a thought experiment made real with modern technology. Led by Wolfgang Ketterle, a Nobel laureate who studies matter at temperatures colder than anywhere in outer space, the team arranged 10,000 ultracold atoms in a precise lattice configuration. These atoms were the slits. They fired single photons through them using a weak laser beam and measured what happened. Then they did something no one had done before with this precision. They could tune how fuzzy the atoms were, how tightly localized in space, using laser confinement. More precise atoms gave up more information about the photon's path. Less precise atoms gave up less. The result, published July 28, 2025 in Physical Review Letters, was decisive. The more the atoms revealed about which path the photon took, the weaker the interference pattern became. When atoms gave up full path information, the interference vanished entirely. When they gave up none, the full wave pattern appeared. Ketterle stated, "What we have done is an idealized Gedanken experiment that Einstein and Bohr could never have imagined performing with single atoms and photons. Einstein was wrong. Bohr was right. You cannot know both the particle and the wave. The act of measurement doesn't just reveal reality, it creates it." And yet simultaneously, while the behavior of light bends to the act of observation, one property of light refuses to yield: its speed. In November 2025, researchers at the Institut d'Estudis Espacials de Catalunya, led by Mercè Guerrero and PhD student Ana Campoy Ordaz, published a study in Physical Review D that tested Einstein's cosmic speed limit at the most extreme scales imaginable. Their method: track ultra-high energy gamma rays from distant astrophysical sources billions of light-years away. Some theories of quantum gravity predict that at extreme photon energies, the speed of light might vary ever so slightly, and over billions of light-years of travel, even a tiny variation would accumulate into a detectable timing difference when different energy photons arrived at Earth. The team combined existing astrophysical measurements using a new statistical technique, testing parameters of the Standard Model extension, the theoretical framework for detecting Lorentz invariance violations. Result: nothing. The speed of light remained constant across all photon energies at a precision 10 times tighter than any previous measurement, improving previous experimental limits by an order of magnitude. This finding was confirmed in January 2026. Einstein's speed of light rule, as one headline put it, had just survived its toughest cosmic stress test yet. The Michelson-Morley experiment of 1887 said light has no medium. The 2025 test says light has no energy dependence. 138 years of increasingly powerful attempts to crack the cosmic speed limit, and C remains unbroken. Stop and hold these two facts together, because the tension between them is where the greatest unsolved problem in physics lives. Fact 1. The behavior of light, whether it acts as wave or particle, is determined by what you measure. Observation collapses the wave function. Reality at the quantum scale is not fixed until someone checks. The MIT 2025 experiment proved this with atomic precision. Fact 2. The speed of light, the fundamental constant c, is absolutely fixed, regardless of measurement, observer, photon energy, or gravitational field. The 2025 and 2026 cosmic tests confirmed this to 10 times higher precision than ever before. One property of light is infinitely malleable, shaped by the act of looking. The other property is the hardest constant in nature, immune to any force. This is not a coincidence. This tension is exactly where quantum mechanics and general relativity fail to talk to each other. Quantum mechanics says reality is probabilistic, observation dependent, fundamentally fuzzy. General relativity says space-time is smooth, C is eternal. The geometry of the universe doesn't care about observers. Most quantum gravity theories, the frameworks attempting to unify these two, predict that at extreme enough energies, even C might wobble, that Lorentz invariance might break, that Einstein's eternal constant might, at the Planck scale, turn out to be an approximation. Every experiment says, not yet, but physicists keep looking, because if they ever found a crack in C, even a deviation of 1 part in 10 to the power of 38, it would be the most important discovery since Newton watched an apple fall.
So why should this matter to you? This is happening in laboratories, in basements, in cosmic observations from billion-dollar telescopes. Why does it change your life? Because the weirdness of measuring light is the engineering foundation of everything around you. Quantum computing, the technology that will eventually crack modern encryption, simulate new drug molecules, and optimize global logistics, is built entirely on the principle that quantum systems exist in superpositions until measured. A qubit is a photon or electron that is simultaneously 0 and 1, a wave, not a particle, until you look at it. The moment you look, it collapses into a definite answer. Quantum computers exploit the time before that collapse to perform calculations that classical computers cannot. Quantum cryptography, the most secure communication system ever devised, exploits the measurement problem directly. A quantum key is encoded in the polarization states of individual photons. If an eavesdropper intercepts those photons to read the key, the act of measurement disturbs the photons and alerts the sender. You literally cannot read quantum information without leaving a trace. The observer effect becomes a security protocol. GPS satellites, fiber optic cables that carry the internet, the solar cells charging your devices, the LED display you're watching this on, MRI machines that image cancer, all of these run on quantum mechanics discovered by asking one strange question: what happens when you measure light? The measurement problem isn't a curiosity from a physics lecture. It is the operating system of the modern world. Here is what makes the 2025 MIT experiment particularly haunting. Ketterle's team didn't just confirm that observation collapses the wave. They showed you can dial it. They could continuously tune the amount of path information available and watch the interference pattern fade in real time, smoothly, as a function of how much the universe knew. This means the boundary between wave and particle isn't sharp. It's a gradient. Reality doesn't snap from quantum to classical in an instant. It bleeds from one to the other as information escapes into the environment. And this raises a question that should make you pause. We, right now, are made of atoms. Those atoms are made of quantum particles. Those particles, when undisturbed, exist in superpositions. They are waves. But we don't experience ourselves as waves. We experience ourselves as definite, located, classical objects. Why? What makes us different from a photon? The answer, physicists believe, is scale and interaction. We are so large, so complex, so constantly interacting with our environment that our quantum information leaks away in a fraction of a nanosecond. Decoherence is so fast and so total that we never experience superposition. But at some level, at the level of your neurons firing, of photons hitting your retina, of electrons jumping between molecules, you are exactly the quantum observer that collapses the wave. You are not just a person watching the experiment. You are the measurement. You are the thing that turns probability into reality. Here is the question that should keep you up at night. We have now confirmed, with the most precise experiments in history, 2 incompatible truths. Measuring light changes how it behaves, but the speed at which it moves cannot be changed by anything. We have tested this with atoms colder than outer space in a laboratory in Cambridge, Massachusetts.
We have tested it with gamma rays from across the observable universe, traveling for billions of years before arriving at a telescope on Earth. Both experiments, in 2025 and 2026, held firm. But we still don't know why. We don't know why observation collapses the wave. We don't know what observation fundamentally means at the level of physics, whether it requires a detector, or a mind, or simply an interaction with any particle in the universe. We don't know if the many worlds interpretation is real, whether right now, in another branch of reality, the photon went the other way, and a different version of you is watching a different version of this video, and the universe is silently, endlessly, infinitely splitting. What we do know is this: every time we achieve a more precise measurement of light, we find a deeper mystery hiding underneath it. The 2025 experiments gave us the clearest view yet of the machinery of quantum reality. The 2026 cosmic tests showed us the speed limit holds at scales beyond imagination. Both answers are extraordinary, but the universe still hasn't told us what any of it means. And that gap between what we can measure and what we can understand might be the most important frontier in all of science.